Do you remember the types of fighter planes that were created during World War II? Leave us a few names that impressed you the most in the comments section. The Messerschmitt Bf 109 dominated the skies of World War II, with over 33,000 units produced, making it the most manufactured fighter aircraft in history at the time. This legendary German fighter aircraft revolutionized military aviation through its groundbreaking engineering innovations and design principles. The engineering brilliance behind the Messerschmitt Bf 109 engine transformed aircraft design standards. From its powerful engine delivering a top speed of over 400 mph to its advanced aerodynamic features, every aspect of the Bf 109 showcased precision German engineering. The aircraft's remarkable power-to-weight ratio, sophisticated weapons systems, and modular construction techniques set new benchmarks in fighter aircraft development. This video will explore the extraordinary engineering achievements that made the Messerschmitt Bf 109 one of the most formidable fighter aircraft ever created, examining its revolutionary design features, performance capabilities, and lasting impact on aviation technology. Revolutionary design philosophy. The engineering philosophy behind the Messerschmitt Bf 109 centered on a groundbreaking approach to aircraft design that prioritized efficiency and performance. At its core was Messerschmitt's lightweight construction principle, which aimed to minimize the number of separate parts in the aircraft. The design team implemented innovative weight reduction strategies through the complex integration of components. Two large brackets fitted to the firewall incorporated both engine mounts and landing gear pivot points into a single unit. This concentrated load-bearing approach allowed for a significantly lighter and less complicated structure compared to contemporary aircraft designs. The landing gear system, which retracted through an 85-degree angle, demonstrated this integration by attaching directly to the fuselage rather than the wings. The Bf 109's aerodynamic design set a new standard in aviation with its innovative wing configuration. Its wings were engineered with precision, featuring an ACA2R1 14.2 profile at the root, where the thickness ratio reached 14.2%, tapering to an ACA2R1 11.35 profile at the tip with an 11.35% thickness ratio. This carefully calculated progression optimized the aircraft's lift-to-drag ratio, contributing to its exceptional performance in high-speed and combat scenarios. To further enhance its aerodynamics, the Bf 109 incorporated opening leading slats, which improved airflow over the wings during critical low-speed maneuvers, such as takeoffs and landings. Large camber-changing flaps on the trailing edges complemented this, allowing for better control and adaptability across various flight conditions. Messerschmitt's design philosophy boldly departed from conventional norms by embracing a higher wing loading exceeding the standard requirement of less than 100 km2. This choice was driven by a focus on high-speed performance, essential for a superior dogfighting edge. While the increased wing loading presented challenges in low-speed handling, advanced design features that underscored the aircraft's engineering sophistication mitigated these challenges. The result was a fighter plane that excelled in agility, speed, and versatility, securing its place as a groundbreaking feat of aeronautical innovation. The structural design of the Bf 109 represented a paradigm shift in aircraft engineering, incorporating several groundbreaking innovations that set it apart from its contemporaries. Central to its design was the use of a single I-beam main spar, strategically positioned aft within the wing. This spar provided the primary structural support while reducing overall weight and complexity. The wing's design also featured a D-shaped torsion box configuration, a clever engineering solution that eliminated the need for a traditional rear spar. This torsion box, formed by the wing skin and internal structure, distributed loads more efficiently, enhancing the wing's strength and rigidity without adding unnecessary bulk. Another significant innovation was the concentration of load-bearing responsibilities within the firewall, the bulkhead separating the cockpit from the engine compartment. By centralizing these forces, the design minimized stress throughout the fuselage and simplified maintenance and repairs. Perhaps the most forward-thinking was the Bf 109's modular construction. This approach allowed key components such as the wings, fuselage, and tail section to be assembled independently before integration into the final aircraft. This not only streamlined production processes but also facilitated easier field repairs and adaptability, crucial factors in sustaining the plane's dominance throughout World War II. The aircraft's structural design allowed for complete wing removal while maintaining fuselage support, a feature that significantly simplified maintenance procedures. This modular approach also facilitated decentralized production and quick replacement of damaged parts in the field. The integration of these design elements resulted in an aircraft that combined exceptional strength with minimal weight. The Bf 109's construction utilized self-supporting half-shells with longitudinal profiles, proving highly stable while maintaining the lowest possible weight. This approach to aircraft design set new standards for fighter aircraft construction and influenced aviation engineering for decades to come. Power and performance engineering. At the heart of the Messerschmitt Bf 109's engineering excellence lay its sophisticated power plant evolution, beginning with the Jumo 210 engine, producing 610 horsepower. The aircraft's engine development journey showcased remarkable advancement in aviation technology, ultimately culminating in power plants capable of delivering up to 2,200 horsepower. The evolution of the Bf 109's power plant marked a remarkable trajectory in engineering sophistication, reflecting continuous improvements in performance and technology. Initially, the aircraft was powered by the Jumo 210 engine, producing 635 horsepower, and paired with a two-blade fixed-pitch propeller. This early configuration provided a solid foundation but left room for significant enhancement as the demands of aerial combat intensified. The introduction of the DEB 601 engine represented a substantial leap forward, with its output increasing to 1,175 horsepower. This engine featured an advanced fuel injection system, enabling more reliable performance during high G maneuvers and negative G conditions, which were critical in dogfighting scenarios. Further advancements came with the DEB 605A, which delivered an impressive 1,475 horsepower. This version incorporated an enhanced supercharger, allowing for superior high-altitude performance and extending the aircraft's operational envelope. The pinnacle of this progression was the DEB 605D engine, capable of producing 1,800 horsepower. This iteration introduced new 50 injection technology, a system that injected a methanol-water mixture into the engine for short bursts of increased power, particularly useful in combat situations requiring maximum thrust. Together, these developments in power plant technology showcased the relentless drive for innovation that defined the Bf 109, ensuring its ability to meet and exceed the evolving challenges of aerial warfare. The Bf 109's propulsion system incorporated several innovative features. The DEB 601 engine utilized a unique barometrically controlled hydraulic fluid flow for its supercharger, which automatically adjusted speed with altitude changes. This advanced system provided superior high-altitude performance compared to contemporary fixed-speed superchargers. A significant enhancement came with the Mu-50 methanol water injection system, which enabled brief periods of emergency power. Combat pilots like Peter Duttman reported that this system proved crucial in critical situations, allowing speeds near 600 km/h at ground level. The system's versatility was demonstrated when pilots discovered that distilled water could substitute for methanol, though this limited high-altitude performance. The Bf 109's power plant optimization yielded impressive performance metrics. The DEB 605 engine integration resulted in maximum speeds between 382 and 415 mph in factory tests. As development continued, later variants of the Bf 109 pushed the boundaries of speed and power even further. The G10 variant, equipped with the refined D605D engine, showcased the full potential of this power plant, reaching an impressive maximum speed of 428 mph. This achievement underscored the relentless drive for technological advancement that characterized the Messerschmitt design philosophy. The pinnacle of this evolutionary journey was realized in the K4 model, which represented the culmination of the Bf 109's engineering advancements. Powered by the DEB 605D engine, and enhanced with methanol water injection technology. This variant could achieve a staggering top speed of 440 mph. The engine's fuel injection system provided a crucial tactical advantage, allowing negative G maneuvers without engine cutout, limitation that affected carbureted engines of the era. This engineering feature gave Bf 109 pilots a significant edge in combat situations, enabling immediate diving maneuvers that their opponents couldn't match. The DB605's sophisticated cooling system included dual radiators with an innovative cut-off mechanism. This engineering solution allowed continued flight for up to 5 minutes, even if one radiator was damaged, significantly enhancing the aircraft's combat survivability. Advanced aerodynamic features. The aerodynamic sophistication of the Messerschmitt Bf 109 manifested in its innovative wing design and advanced lift enhancement systems. The aircraft's wing architecture represented a significant departure from conventional designs of its era. The wing's foundation rested on a pioneering single I-beam main spar configuration, positioned further aft than typical designs to accommodate the retracted landing gear. This arrangement created a robust D-shaped torsion box that eliminated the need for a rear spar, marking a departure from the dual spar designs common in contemporary aircraft. The Bf 109's automatic leading edge slats, based on Sir Frederick Handley Page's 1919 patent, represented a masterpiece of aerodynamic engineering. These devices extended automatically under aerodynamic pressure during high angles of attack, channeling airflow over the wing's upper surface to maintain lift effectiveness. Throughout the Bf 109's production, the slat mechanism underwent significant evolution to enhance its functionality and reliability. Early models, such as the E and F variants, utilized a swing-arm parallelogram mechanism with a slat span of 2,292.5 mm. This configuration effectively maintained the desired aerodynamic flow, but presented challenges in terms of structural complexity. From the F variant onward, a modified design reduced the slat span to 1,800 mm. This adjustment streamlined the mechanism and improved its integration with the wing structure, balancing performance with manufacturability. The G series introduced a roller track system, a further refinement that not only enhanced the reliability of the slat operation, but also reduced maintenance demands. This innovative mechanism ensured smoother and more consistent deployment, a crucial factor during the high-stress conditions of aerial combat. By continuously refining the leading-edge slat design, the Bf 109's engineers demonstrated a commitment to maximizing the aircraft's aerodynamic efficiency. These advancements not only contributed to the fighter's agility and maneuverability, but also underscored its reputation as a masterpiece of engineering tailored to dominate the skies. The aircraft's airflow management incorporated multiple sophisticated elements working in concert. The wing's higher loading design, exceeding the standard requirement of 100 km/h, prioritized high-speed performance. To compensate for this increased wing loading, Messerschmitt implemented an integrated system of high-lift devices. At the forefront of these innovations were the leading-edge slats, a groundbreaking feature that significantly enhanced the aircraft's lift capabilities. These slats were designed to deploy automatically under aerodynamic pressure, extending during high angles of attack such as steep climbs or sharp turns. By redirecting airflow smoothly over the wing's upper surface, the slats prevented the onset of airflow separation, thereby maintaining lift effectiveness. This automatic deployment system not only improved the aircraft's horizontal maneuverability, but also allowed pilots to execute precision maneuvers with confidence, even at lower speeds or higher altitudes. Complementing the leading-edge slats were the trailing-edge systems, which played an equally vital role in the Bf 109's performance. Large camber-changing flaps on the trailing edge adjusted the wing's curvature, optimizing lift during takeoffs, landings, and low-speed flight. These flaps were further augmented by drooping ailerons, which coordinated their movements with flap deployment to increase the effective wing area. This synergy between the flaps and ailerons improved overall stability and control, compensating for the high wing loading and ensuring smooth, predictable handling even in challenging conditions. The integration of these aerodynamic features resulted in exceptional high-speed performance while maintaining controllability at lower speeds. The automatic slat system particularly distinguished itself by increasing the wing's lift coefficient significantly during high-angle maneuvers, though pilots needed to adapt to their automatic deployment characteristics during combat situations. Weapons integration engineering. The weapons integration of the Messerschmitt Bf 109 exemplified German engineering precision through its sophisticated centralized armament system. The aircraft's weapons configuration evolved significantly throughout its operational life, adapting to combat requirements while maintaining exceptional performance characteristics. Messerschmitt's design philosophy emphasized low-weight, low-drag configurations by centralizing the primary armament in the fuselage. The initial design featured two synchronized 7.92 mm MG-17 machine guns mounted in the cowling, firing over the propeller arc. This arrangement maintained the wing's thin profile, crucial for the aircraft's performance envelope. The armament evolved through several configurations. The E-1 variant introduced supplementary firepower with two additional MG-17 machine guns mounted in the wings, providing increased offensive capability without significantly compromising the aircraft's performance. The E-3 model marked a further advancement by replacing the wing-mounted machine guns with mere MGFF cannons, delivering more destructive power against armored targets and enemy aircraft. The F-Series represented a significant leap in firepower innovation. This variant replaced the wing-mounted armament entirely with a single 20mm Motorkanone cannon firing through the engine's propeller hub. In the G-Series, Messerschmitt took armament capabilities to new heights. The cowling-mounted machine guns were upgraded to two 13mm MG-131 heavy machine guns, delivering greater firepower and range. Additionally, the Motorkanone was replaced with a formidable 30mm Mk108 cannon. The synchronization system of the Bf 109 was a groundbreaking innovation in aviation engineering, showcasing the meticulous attention to detail that defined the aircraft's design. This sophisticated mechanism allowed the Bf 109's weapons to fire through the spinning arc of the propeller without damaging the blades, a critical feature that preserved both the aircraft's firepower and structural integrity. Unlike earlier mechanical systems, which relied on complex gears and linkages, the Bf 109 employed a more advanced electrical synchronization system that was both reliable and precise. In its initial iterations, the system was tailored to control the firing of percussion-primed 7.92mm MG-17 machine guns mounted in the engine cowling. Electrical control provided a significant advantage by ensuring that each weapon discharged at exactly the right moment, timed perfectly with the propeller's rotation. This not only eliminated the risk of striking the propeller blades, but also allowed for consistent, uninterrupted fire during combat. As the Bf 109's armament evolved, so too did its synchronization system. Later models incorporated the larger and more powerful 13mm MG-131 heavy machine guns, which utilized advanced electrical priming technology. This upgrade represented a major leap in synchronization capabilities, as the system had to accommodate the increased complexity and power requirements of these weapons. Despite these challenges, the engineers refined the mechanism to maintain seamless operation, ensuring that the aircraft's offensive capabilities remained at the cutting edge of technology. One of the most impressive aspects of the Bf 109's synchronization system was its ability to achieve higher firing rates through precise timing control. By leveraging the accuracy and responsiveness of electrical systems, Messerschmitt engineers minimized delays and maximized the efficiency of the firing cycle. This high level of precision was vital in dogfights, where split-second timing could determine the outcome of an engagement. The Bf 109's synchronization system was not merely a technical solution, but a testament to the innovative spirit of its creators. By integrating advanced electrical technology into the aircraft's design, they ensured that the Bf 109 could deliver its devastating firepower with unparalleled precision and reliability, securing its place as one of the most formidable fighter aircraft of its era. The engineering team developed innovative solutions for ammunition supply challenges. For wing-mounted weapons, they created an unusual feed system that maximized ammunition capacity without compromising the wing structure. The system featured, including a continuous belt holding 500 rounds, complex feed chutes extending to wing tips, roller systems at wing roots and tips. The centralized fuselage guns carried substantial ammunition loads with 1,000 rounds per gun. Later variants introduced conformal gun pods under the wings, weighing 135 kg excluding ammunition, which could carry 135 to 145 rounds per gun. While these additions enhanced firepower, they imposed a speed reduction of 8 km/h and affected handling characteristics. The motor cannon configuration, firing through the propeller hub, initially faced technical challenges but evolved into a reliable system in later variants. This arrangement proved particularly effective against bomber formations, though some leading pilots like Adolf Galland initially criticized the reduced overall firepower compared to wing-mounted configurations. Cockpit and control systems. Inside the Messerschmitt Bf 109's compact cockpit, German engineers crafted a sophisticated control environment that balanced automation with pilot accessibility. The aircraft's cockpit design represented a careful compromise between space efficiency and operational functionality. The Bf 109's cockpit layout prioritized essential controls within the pilot's immediate reach, though space constraints posed significant challenges. The cockpit's dimensions proved notably restrictive, with pilots reporting the narrow width particularly challenging during extended missions. The seat design featured 3 adjustable positions, though the deep-set configuration required pilots to maintain a lower sitting position than typical for fighter aircraft of the era. Key cockpit features included height-adjustable bucket seat, centralized engine instruments, left-side throttle quadrant placement, and undercarriage controls near throttle. The Bf 109's control systems demonstrated a sophisticated approach to aviation engineering, integrating automation to enhance performance while reducing pilot workload. At the heart of this innovation was the DB605 engine, whose advanced control linkages allowed for the seamless management of multiple interconnected systems. These automated features optimized the aircraft's performance across various flight conditions, showcasing a level of engineering sophistication ahead of its time. One of the key automated systems was the supercharger, which utilized barometric control to adjust its operation based on altitude. This ensured consistent engine performance and power output, regardless of changes in atmospheric pressure, a critical advantage during high-altitude combat. Similarly, the aircraft's radiator system was designed to self-adjust, modulating airflow through the radiators to maintain optimal engine temperature without requiring constant pilot input. The propeller's RPM was governed automatically, allowing the engine to operate at its most efficient speed for any given throttle setting. This feature not only enhanced performance but also reduced strain on the engine, extending its operational life. Additionally, the fuel mixture control was self-regulating, ensuring the correct air-fuel ratio for varying altitudes and engine loads, thereby optimizing both power and fuel efficiency. Despite the sophistication of these automated systems, the Bf 109 retained manual override capabilities for all critical functions. This dual approach allowed pilots to assume direct control when necessary, such as during emergencies or when precise adjustments were required in combat. In terms of trim systems, the Bf 109 deviated from traditional designs. Instead of adjustable in-flight trim tabs, the aircraft utilized ground-adjustable settings that were calibrated to match the optimal cruise speed. This unconventional choice reflected Messerschmitt's emphasis on streamlining the aircraft's design to reduce drag and improve overall performance, particularly during high-speed operations. Together, these automated and manual features exemplified the Bf 109's blend of cutting-edge technology and pilot-centered design. The result was an aircraft that combined advanced engineering with operational flexibility, contributing to its reputation as one of the most innovative and effective fighter planes of its era. Early Bf 109 variants struggled with visibility limitations, particularly during ground operations. The combination of a deep-set cockpit position and heavy framing significantly restricted pilot sight lines. Recognizing the critical nature of these visibility limitations, Messerschmitt's engineers focused on making significant improvements in later Bf 109 variants. One of the most important modifications was the introduction of the airler canopy, which enhanced side visibility. The new design was a major step forward, offering a more streamlined and less obstructed view, especially when maneuvering on the ground or during combat. In addition to the airler canopy, the engineers also modified the canopy framing itself, reducing the size and number of structural elements that created blind spots. Further enhancements were made to the quality of the canopy glass. The new glass was of higher optical clarity. The G10 variant marked a significant advancement in cockpit ergonomics, incorporating refined aerodynamics and improved flight controls. Despite these enhancements, the fundamental space constraints remained a characteristic feature of the aircraft's design, influencing pilot comfort and operational effectiveness throughout its service life. Manufacturing innovation. Production engineering of the Messerschmitt Bf 109 showcased remarkable innovation in aircraft manufacturing, establishing new standards for fighter aircraft assembly. The manufacturing process combined efficiency with precision, resulting in the production of 34,248 units between 1936 and 1945. The Bf 109's manufacturing philosophy centered on a revolutionary split fuselage design. Engineers developed a monocoque fuselage divided into two halves, joined using flush rivets, creating a robust foundation for component installation. This approach offered several advantages, such as quick assembly and disassembly for maintenance, simplified component replacement, enhanced structural integrity, and streamlined production process. The central fuselage section featured exceptional structural strength, providing superior crash protection while maintaining efficient assembly characteristics. The wing attachment utilized 4 strong bolts, enabling rapid wing replacement during maintenance or repair operations. The Bf 109's production efficiency was unparalleled, driven by a series of innovative manufacturing techniques that allowed for rapid and large-scale production. These advancements played a key role in meeting the high demand for aircraft during World War II. Between 1936 and 1945, a total of 34,248 units were produced in Germany, showcasing the remarkable scale of the aircraft's manufacturing operation. Following the war, production of the Bf 109 continued in Czechoslovakia, where an additional 600 units were built, and in Spain, which produced 200 more. The aircraft's modular design was a critical factor in the success of its widespread manufacturing. This design approach allowed for components to be produced independently across various facilities, making it easier to meet the demands of wartime production. The modularity of the Bf 109 meant that each facility could specialize in producing specific parts, which were then assembled at central locations, streamlining the entire process and reducing production time. In 1944 alone, nearly 14,000 Bf 109G variants were manufactured, accounting for approximately 25% of all Luftwaffe aircraft production that year. This massive output played a crucial role in sustaining the Luftwaffe's aerial capabilities despite mounting challenges. In addition to the modular design, the Bf 109's manufacturing process incorporated several features that facilitated rapid assembly and efficient maintenance. One of the most notable innovations was the quick-release engine mounting system, which allowed for faster engine swaps and repairs, minimizing downtime for maintenance. This system was particularly beneficial during combat operations when the aircraft needed to be quickly prepared for the next mission. The aircraft's panel design was also engineered for ease of removal. This feature simplified access to critical components, such as the engine avionics and armament systems, enabling quicker repairs and reducing the time required for routine maintenance. The thoughtful design of these removable panels ensured that even under combat conditions, technicians could quickly and effectively perform necessary maintenance to keep the aircraft operational. Further enhancing efficiency, the Bf 109 incorporated standardized component interfaces. This standardization allowed for greater interchangeability of parts, which not only sped up the assembly process but also facilitated repairs in the field. If a component failed, it could be easily replaced with a compatible part, ensuring that the aircraft could return to combat as quickly as possible. Overall, the Bf 109's manufacturing process reflected a high level of ingenuity and adaptability, enabling the aircraft to be produced at a scale and speed that was critical to the success of the Luftwaffe during World War II. By optimizing both assembly and maintenance, Messerschmitt ensured that the Bf 109 remained one of the most effective and versatile fighter aircraft of its time. Material selection played a crucial role in the Bf 109's manufacturing success. The aircraft's skin utilized duralumin, an advanced aluminum alloy providing optimal strength-to-weight characteristics. The engineers also paid particular attention to the wing structure, opting for a more efficient design that deviated from traditional dual-spar configurations. Instead, they used a single, strategically positioned wing spar located toward the rear of the wing. This departure from conventional designs not only saved weight but also helped streamline the wing's construction, offering a better overall balance of strength and aerodynamics. The choice of materials for the wing components was equally strategic, with lightweight alloys being used that could tolerate high stresses without compromising structural integrity. This allowed the aircraft to endure the forces experienced during high-speed maneuvers or combat situations, while maintaining an efficient and responsive flight performance. Further, the Bf 109's engine mounts were designed with efficiency and practicality in mind. The Y-shaped metal bars used in the engine mount incorporated quick-release mechanisms, allowing for faster engine changes and reducing the time needed for maintenance. This design feature was crucial in ensuring the aircraft could be rapidly prepared for combat, especially when quick repairs were necessary between missions. The control surfaces of the Bf 109 were also constructed with careful consideration to material selection, ensuring that weight distribution was optimized for both stability and maneuverability. The engine installation exemplified this material-conscious design, featuring easily accessible panels and a junction box system for electrical connections. This approach facilitated rapid engine maintenance or replacement, crucial for combat operations. The fuel tank design similarly reflected material optimization, utilizing an L-shaped configuration with a 250-liter capacity, accessible through a simple wing center cover. Engineering challenges. Despite its revolutionary design, the Messerschmitt Bf 109 faced several significant engineering challenges that impacted its operational effectiveness. These technical hurdles required careful consideration and ongoing refinements throughout the aircraft's service life. The Bf 109's landing gear configuration presented one of its most notable engineering challenges. The narrow track width, measuring just 2.06 meters for the G series, combined with long, splayed legs, created inherent stability issues. While the Spitfire had an even narrower track at 1.68 meters, the Bf 109's unique combination of design elements proved more problematic. The landing gear's key challenges included outward splayed legs transferring landing loads at angles, poor forward visibility during ground operations, and significant sideways drift during takeoff due to propeller torque. These design compromises resulted in substantial losses, with approximately 10% of all Bf 109s lost in takeoff and landing accidents between 1939 and 1941. Recognizing the severity of these issues, engineers focused on making continuous improvements to address the aircraft's ground handling limitations. One of the key changes was the introduction of larger main wheel tires, implemented in the G series and subsequent variants. This modification was aimed at enhancing the stability of the aircraft during takeoff and landing, reducing the likelihood of accidents caused by poor traction or instability on the runway. The enlarged tires provided better support and allowed for smoother ground handling, especially on less than ideal surfaces. In addition, the tail wheel was enlarged in the late G10 variants to further improve the aircraft's ground handling capabilities. The larger tail wheel allowed for better control during taxiing and helped prevent the aircraft from tipping backward during takeoff or landing. This enhancement significantly improved the overall safety and operational efficiency of the Bf 109 when on the ground. Another important modification was the adjustment of wheel mounting angles, particularly in the K series. By altering the angles at which the wheels were mounted, engineers were able to reduce stress on the landing gear legs. This not only improved the durability and reliability of the landing gear, but also contributed to smoother landings, reducing the risk of gear failure or other related issues. Through these incremental changes, Messerschmitt engineers were able to address the Bf 109's ground handling deficiencies, making the aircraft safer and more stable during takeoff, landing, and taxiing operations. While the initial design challenges led to significant losses, these improvements ensured that the Bf 109 remained a formidable fighter aircraft, both in the air and on the ground. The Bf 109's fuel system engineering faced significant operational constraints. The primary fuel tank's L-shaped configuration, positioned partly under the cockpit floor and behind the rear bulkhead, created unique challenges for fuel delivery. The booster pump system required precise management, particularly during high-power operations with Mu-50 methanol water injection active. The complexity of the Bf 109's fuel system resulted in several technical challenges. One of the key issues was the fluctuation of fuel pressure during high-power operations, which could disrupt engine performance, especially under demanding conditions. Additionally, the fuel system featured complex pump selector mechanisms that required careful and precise management to ensure the correct fuel flow was maintained. Another limitation was the aircraft's relatively small fuel capacity, which restricted its operational range and required pilots to carefully manage fuel usage during missions. Furthermore, maintaining consistent fuel pressure during combat maneuvers was critical, as any drop in pressure could cause engine instability or power loss at crucial moments. While the Bf 109's design prioritized maintenance access, certain compromises affected service efficiency. The engine mounting system utilized two large, forged electron magnesium alloy Y-shaped legs secured by quick-release fittings on the firewall. This arrangement facilitated rapid engine changes but presented its own set of challenges. The maintenance system incorporated several innovative features, such as color-coded pipe connections grouped in central locations, quick-release panels for essential system access, electrical equipment concentrated in firewall junction boxes, and modular component design for rapid replacement. However, these advantages came with trade-offs. The narrow fuselage design restricted access to certain components, and the complex landing gear system required frequent maintenance attention. The splayed gear legs were particularly susceptible to damage during heavy landings, necessitating regular inspection and repair. The aircraft's maintenance requirements intensified as later variants incorporated additional systems and armament. Field mechanics needed to balance the benefits of the quick access panels and modular design against the increasing complexity of the aircraft systems, particularly in the G and K series variants. Performance evolution. The technical evolution of the Messerschmitt Bf 109 marked a continuous pursuit of enhanced performance through systematic engineering improvements. From its initial combat deployment to its final variants, each iteration pushed the boundaries of fighter aircraft capabilities. The Bf 109's performance progression demonstrated remarkable advancement across its operational life. The E-series achieved a maximum speed of 350 miles per hour with a ceiling of 36,000 feet. Subsequent variants of the Bf 109 saw continuous performance improvements. The E-series, equipped with the DEB6-01 engine, achieved a maximum speed of 350 mph, marking an early leap in power. The F-series followed, reaching 390 mph, thanks to enhancements in aerodynamics that improved its overall efficiency. The G10 variant pushed the speed further, reaching 428 mph with the more powerful DEB6-05D engine. The K4 model achieved a top speed of 440 mph, driven by the addition of Mu-50 injection, which significantly boosted the engine's performance. The aircraft's maneuverability characteristics evolved through careful engineering refinements. The F-series introduced extensive aerodynamic improvements, including enhanced cooling systems, refined flaps, and modified slats and ailerons. These changes significantly improved both maneuverability and climb rate performance. Throughout the development of the Bf 109, high-altitude performance remained a primary concern for engineers, who introduced a range of innovative systems to address this challenge. One of the key advancements was the integration of the GM1 nitrous oxide injection system, which provided a power boost at higher altitudes, compensating for the reduced air density. Additionally, the introduction of a pressurized cockpit in the G1 variant played a vital role in improving pilot efficiency by ensuring a stable and breathable environment even at extreme altitudes, reducing the physical strain on the pilot. Furthermore, the late G-series models featured the D605's engine, equipped with an enlarged supercharger, which enhanced engine performance in thin air, ensuring the aircraft maintained its power and effectiveness during high-altitude operations. The aircraft's service ceiling showed steady improvement, reaching 41,339 feet with the D605 engine. This enhancement represented a significant advance over the E-series' 36,000-foot ceiling. The pressurized cockpit system, particularly in the G1 variant, proved highly effective, allowing pilots to operate efficiently at extreme altitudes. Combat effectiveness evolved through a combination of performance improvements and tactical advantages. The Bf 109E demonstrated superiority over all opposition until May 1940. The fuel injection system provided a crucial tactical advantage, allowing negative G maneuvers without engine cutout capability that carbureted engines of opposing aircraft lacked. The F-series marked a significant advancement in combat capability, achieving superiority over the Spitfire V in Western theater operations, Allied fighters in North African campaigns, and Soviet aircraft during initial Eastern Front operations. Later variants incorporated additional combat performance enhancements. The G-series, while heavier than its predecessors, maintained competitive performance through power improvements. The D605D engine, when combined with Mu-50 methanol water injection, achieved emergency power outputs of up to 1,800 horsepower. The Bf 109's combat effectiveness was significantly enhanced through the ongoing development of its power plant systems. The introduction of the DED-601N engine during the Battle of Britain marked a key milestone, offering improved high-altitude performance. Over time, several additional engine advancements were implemented to further boost the aircraft's capabilities. One of the major improvements was the integration of the Mu-50 water methanol injection system, which provided a boost at low and medium altitudes, enhancing overall performance. Additionally, the aircraft's supercharger systems were refined, leading to better altitude performance, while the cooling systems were upgraded to sustain high power outputs during extended operations. Operationally, the engine saw continuous improvements with more refined control systems and advanced fuel delivery mechanisms, ensuring a smoother and more efficient operation. The final K4 variant represented the pinnacle of Bf 109 performance engineering, combining all previous improvements with the most powerful engine variant. This model achieved the highest speed of any Bf 109 variant at 440 mph, while maintaining the aircraft's characteristic excellent climbing and diving capabilities that had defined its combat effectiveness throughout the war. The Messerschmitt Bf 109 stands as a prime example of German engineering brilliance during World War II. With its lightweight construction, advanced aerodynamics, and powerful engines, it achieved remarkable performance improvements throughout its development, reaching speeds of 440 mph in its final K4 variant. Despite operational challenges such as narrow landing gear, the aircraft's innovative features like automatic leading-edge slats and centralized weapon systems set new standards in fighter design. The Bf 109's legacy continues to influence modern aviation, showcasing the power of breakthrough engineering. What do you think about the Bf 109's engineering? Comment with your ideas here. Comment 1 if you like this video. Thanks for watching, and see you again in the next video.